Follow along with me to make your first FPGA application. Here's what we will make in this project. On the FPGA target, a VI to blink the LEDs and read the onboard button. On the desktop, a testbench VI for interactive simulation of the FPGA VI. On the RT target, a startup application to run the FPGA VI and interact with the desktop computer running the Human-Machine Interface, or HMI. We will build this application in 9 steps. First, create a new LabVIEW project. Then create FPGA Main VI. Create the FPGA testbench VI. Interactively test and debug FPGA Main. Compile FPGA Main to a bitstream file. Create and deploy shared variables on the RT target. Create RT Main. Create PC Main. And finally set RT Main as the startup VI. If you like, see the video description page to download the completed LabVIEW project. Let's begin by creating a new LabVIEW project. I've just started LabVIEW. Select File, New, and then Empty Project. We'll go ahead and save this newly created file. Choose a folder where the project and all of the associated files will be housed. I'll call this First FPGA Application. Now I'm adding the academic Rio device. I already have this connected, so I'm using the Discover technique. Select the device. In my case, it's my Rio. You may wish to rename the device if you like. Now I'll minimize the details that we don't need to see right now. Asterisk indicates that the file is not current. Let's go ahead and save it. Now let's create the FPGA Main VI. Select the FPGA target, New VI. Begin by saving this away. I'll call this FPGA Main. Let's modify the icon to reflect the name of this VI. Alright, let's display this in tile mode. This way we can see the front panel and the block diagram at the same time. I'm going to expand the zone for the onboard I/O and place an FPGA I/O node for button 0. Also going to place a Boolean front panel control. Activating either one of these will pause the LED blinker. We'll connect those together by what will amount to an OR gate on the FPGA fabric. I'm placing a feedback node, and especially when you flip the direction like this, you can now view this as a flip-flop, because that's what it will be on the FPGA fabric. The exclusive OR serves as a selectable inverter. So we take the present state of the flip-flop, feed that back around, and then depending on the second input of the XOR gate, it will allow the output of the flip-flop to toggle or to remain in the same state. Here's the FPGA I/O nodes for the onboard LEDs. It's easy to align the elements on the block diagram or the front panel, so we'll align by all their edges. Now, the flip-flop is connected directly to LED 2, the inverted version of that to LED 3, and I'm using LED 1 to watch the pause state. These front panel indicators will show the paused state as well as the state of all of the LEDs. Hold down the control button and then click and drag to do the copy like I just did. I'll rename these LEDs A and B. And I'm just placing these next to their associated FPGA I/O node. Now I'll wrap the whole thing in a while loop. Most often on an FPGA, you simply wire the stop button to a false. That way the loop just runs forever. Would like to be able to control the iteration time. We'll do this in terms of milliseconds. And create a front panel control. That way we can manipulate the blink rate. We'll call this loop time in milliseconds. I'll finish the front panel by giving it a title, FPGA Blinker. Select the text, then Control 0, and then you can select the font size. You could also adjust things like boldface and so on. Hold down Control and Shift to move the elements in a group like I just did, and then we can size the window. Doing the same thing over in the block diagram. Subdiagram labels are nice. Let's call this process loop number 1. And I've opened up some room so we can make a second process loop. Double click and start typing, and that's how you can add a text label. My second process loop will be a little bit of code that will blink the LED once every second. And it will do this with a relatively short duty cycle. That is, the on time will be shorter than the off time. I'm constructing a down counter. And when the count value reaches 0, it loads a constant. We'll have to update that constant in just a moment. But if it has not yet reached 0, then we decrement the count value. We have a 40 megahertz clock. That's 40 million cycles per second. So we'll load or reinitialize the counter to 1 less than 40 million. Therefore, the counter passes through 0 exactly once per second. On the way down to 0, anytime the counter is 5 million or below, we'll use this to activate LED 0. And this means that the LED will blink for 1/8 of a second every second. Grab a copy of the FPGA I/O node and select LED 0. Now for the second process loop, I'll illustrate using a timed loop. And by default, this uses the 40 megahertz clock in ticks. Wire that to a false constant, and this one iterates once every clock tick at this rate of 40 megahertz. Add another descriptive label here, and you could also use a subdiagram label as I did above. Now let's go ahead and create a so-called testbench VI. This is a VI that runs on the desktop computer. So we'll select my computer and then choose New VI. We'll name this FPGA Testbench. I'll fix up the icon name again, remind ourselves of what this VI is all about. And the test bench gives us the ability to simulate the FPGA VI and do development and debugging very rapidly without incurring the cost of compiling to a bitstream file every time you want to see the effect of a change. The heart of this is the desktop execution node. select the FPGA VI that you are going to work on. You can select its front panel controls and indicators. I'll use all of them. And then you can also apply simulated I/O directly to the FPGA inputs and outputs. We'll need these 4, and the LEDs are all output direction exclusively. We'll need to create a control for each of the 3 inputs. And then I'm going to make a little decoration here. This is the rounded box. And this will help us to keep straight the difference between the front panel controls and indicators and then the FPGA I/O nodes. Okay, those are hidden behind. Select the little panel and say move to the back. Doing a Control Shift on that one to copy. Again, we'll do a Control Shift J to send that one to the back. Let's give this a title as we've done before. Control 0, and then select the new font size. I'm going to create an indicator for each one of these outputs. And I think it'll be more convenient to see these 4 LEDs grouped together as a single Boolean array indicator. So that's LED 0 to 3, 0 being on the left and then 3 on the right. There we go. LED 0 to 3 is one of the onboard devices, and then we'll get the front panel indicators where they belong as well. We'll wrap this into a while loop and create a stop button. So that way we can stop the VI conveniently. And I'll paste this with the wait function, and we'll set this up for 100 milliseconds per iteration. This way it's polling the front panel controls at the rate of 10 Hertz. All right, finish up then by selecting Control S to save it. Now let's begin the testing and debugging process. I'll open up the front panel of FPGA Main, identify the target, and choose simulation mode using simulated I/O. And let's start up the test bench. Each time the desktop execution node runs amounts to 1 clock tick on the FPGA. Therefore, setting the loop time in milliseconds to 0 is really the best option for us. So trying out both the virtual onboard push button as well as the front panel control, and we see evidence of blinking, but the pause mechanism is working opposite the way it should. Trouble spot is right here. This OR gate should really be a NOR gate to work properly. So what I'll do is keep the OR gate in there so we can see the paused state showing up properly on the LEDs, but then I'll insert an inverter right there. Okay, good. There's the correct behavior. Once the VI has been thoroughly debugged in simulation mode, it's time to compile this to a bit file so it can actually run on the FPGA target. Click Run to start this process, and because the bit file does not exist, you are prompted to select your compiler. Use your local compile server to run it on your own desktop. This process will take on the order of 4 to 5 minutes. I'll go ahead and close this dialog and let it run in the background. Now let's create and deploy some shared variables to be hosted on the RT target, or the real-time target. Select the target and choose New Variable. I'm going to create a set of variables to correspond to the front panel indicators and controls of FPGA Main. So for example, LED A is a Boolean. You'll notice that a default library has been created for this variable. You can then select the library and choose New Variable to create another one. We'll call this LED B. This is also of type Boolean. And you can do that a few more times for the other Booleans, as I've done here. And then the one that's different is the loop time. This one has a data type of unsigned integer 32 bits. Now when you save the project, you get a prompt about the library. And try to choose a meaningful name for this one. I'll go with the name that matches the name of the project. So this is First FPGA App. Once the variables exist in the project, we can deploy them on the real-time project so that other systems can access them through the network. The network address when you're connected by USB LAN is 172.22.11.2. We then say deploy all the variables in this library. Once deployed, these variables are always available to other systems on the network, even when the academic Rio device is power cycled. Let's take a look at these through the Distributed System Manager. Look under Network Items. There's the IP address we just typed in, and we see the library name and the variables underneath. And this is reporting the actual state of each one of these variables. You can use the Distributed System Manager to set values of these variables too. All right, let's start working on the code that runs on the real-time target. Select the real-time target, choose New VI. I'll give this the name RT Main. Change the icon as we've done before to read RT Main. I see the compile server has just finished its work. That means the FPGA bitstream file is ready to go. I'm going to begin by placing a flat sequence structure. We'll give this 2 panels. In the first panel, we'll initialize the shared variables, change the access mode to write, and then create the constant. So we'll initialize loop time to 100 milliseconds. Use a sub-diagram label to give a little bit more indicator of what's happening in each part. We'll select the others that need to be initialized as well. That would be pause and stop. Now in the main section of the code, we'll begin by creating a reference to FPGA Main, and then this will also load and run the FPGA bit file. We'll use the read-write control node to establish communication with the FPGA VI through its front panel controls and indicators. So we wire in the FPGA reference, and then we can select one or several or all of the front panel controls and indicators. Each time that this read-write control node runs, it accesses the front panel of the FPGA VI. Incidentally, to open up more spaces I just did, hold down the control button and then shift and drag with your left mouse button. So here I'm establishing the connections between the FPGA front panel controls and indicators and their corresponding shared variables. Now add a while loop, and on each iteration of the while loop it will access the front panel controls and indicators of the FPGA VI, and will stop this loop according to this shared variable. Insert a wait function so that the read-write control node does not run too quickly. In this case, it polls once every 100 milliseconds. Once we break out of this loop, we'll close the reference to the FPGA VI, and then by default, it also stops the VI from running. We'll go ahead and save that. And I notice there's just a little bit more wiring that needs to be done. We'll give this a name on its front panel. And I think we're all set. Let's give it a try. All right, looking at the behavior on the onboard LEDs, everything looks reasonable. I'll show you how you can access the shared variables using the distributed system manager. Okay, I've paused the blinking. Let's try setting a longer loop time. This will slow down the blink rate. We'll turn the pause control off, and sure enough, LED 2 and 3 are blinking slower than they used to. Let's also try the onboard button, pressing that right now, and that's working fine. Finally, select the stop shared variable, set that to true, and the VI shuts down, and the FPGA VI resets itself, and all the LEDs go dark. Now let's move on to the third and final VI. This is the human-machine interface that runs on the desktop computer. Creating a new VI, we'll call this PC Main. As before, I will edit the icon, call that PC Main. And I'll begin by creating a series of front panel indicators and controls. We have pause button and then 3 LED style indicators using a horizontal slide pointer, and this will be for setting the loop time. This needs to be an unsigned integer of 32 bits. Let's have the slider run between 10 and 1000. Make the digital display available so that way you can type in a specific number. And then select this control and choose Edit, Make Selected Values Default. That way, when the VI is first opened, the loop time defaults to 100 milliseconds. Use a slightly different style for this push button to stop the RT main VI from running. And tidy that up a little bit and give it a name. All right, let's get all of these situated together and aligned. Now, all of these front panel controls and indicators can remain in their own area of the block diagram. They don't need to be connected to anything because we are going to bind them directly to the shared variables hosted on the real-time target. Let's see how to do that. Select the properties, choose data binding. We're looking for the shared variable engine, and then browse for network items to the IP address that we entered earlier, and then find the library and then the shared variable of interest. we only need to write to this variable, and that takes care of the first one. There's another way to do this. You can use the shared variable editor. That's the one we just did. So we could choose a different one. And in a similar fashion, we can choose the network items, and then the IP address, and then the shared variable. Select the appropriate mode, and so on. So you do that. You can do that for each of the remaining ones. Once you've done that, select Apply, and then Close. You'll notice now that each indicator has the little flag attached to it. The stop does not yet have one. Looks like I forgot that one. I'll go ahead and do the properties technique for that. All right, that looks good. Now the rest of the VI is pretty simple. I'm going to create an idle loop that just keeps the VI running, so that way the bound indicators will work properly, and it just keeps it running until we click a stop button. So I've placed a while loop, and then I'm placing an event structure. Let's create a stop button, and then we'll set that as the event that's handled by the event structure. Select the stop button and then select OK. You'll want to move the stop button inside. And let's clean up that wire right there and give it a little bit of a description. This idle loop consumes basically 0 CPU resources because the event structure blocks until the stop button is clicked, and at that point it emerges from the event structure and stops the loop. All right, I think we're ready to give this a try. I'll start up RT main. Okay, there's the expected behavior. Let's start up the PC main. We see all the bound indicator flags have gone green, indicating that they have successfully connected across the network to the shared variables on the real-time target. And here you can control remotely through the network the behavior of the RT main application that's running on your academic Rio device. I'd like to point out that the RT main is still running, even though the desktop VI has stopped. Let's restart this one again. And I'm going to click that one. That one stopped the process running on the real-time target. We see all the LEDs have gone dark. And then I can stop the desktop VI. Let's take just a moment with the distributed system manager here, just to emphasize the point that the desktop VI is directly interacting with the same shared variables that are hosted on the real-time target. I think I have to move some things around here a little bit. There we go. So again, as you manipulate the control on the desktop, you see the value is updating. All right, let's finish up by setting RT main as the default startup VI. And that way it will run when the academic Rio device powers up or reboots. So we're back in our Project Explorer window, looking for a new build specification, and you're welcome to use a different name there. I'll just go with the default. We can take the defaults for pretty much everything and find RT main and designate that as the startup VI. And click Build, and that compiles code and gets it ready to install on the real-time target. Choose Run as Startup. And you'll need to log in with your admin credentials. And once you've done that, the code is downloaded and designated as the startup VI. The device reboots. We see the status light goes orange for a moment. And then there it goes. There's a startup VI running just after the reboot. Let's try our human-machine interface again. Successfully connected. And again, we've got full command and control of the real-time startup VI. RT main continues to run even though the remote interface has stopped, and it will continue to do so until something causes it to stop, such as enabling the shared variable. Well, congratulations, you've now constructed your first complete FPGA-based LabVIEW application.